Hey, what's going on, everybody? This is Jason Dinsmore from OrganicChemistOnCall.com. What I'm going to talk to you about today is hybridization, so sp3, sp2, and what that's all about. So when we think about, let's just take the simple molecule that you'll typically see when you start organic chemistry, see it over and over again through the class, is this methane. So 1 carbon, 4 bonds. The way that we draw it in the book, or the books draw it, is something like this, where it looks like we have a 90-degree angle between all of those. Now, as we've talked about before, in order to get electrons to, when we talked about single and double bonds, or double bonds specifically, we said that we wanted the electrons of the single bond in the double bond and the pi bond in the double bond to be 90 degrees from each other, because that kind of maximizes the space, the distance away from each other, since electrons don't want to be, sets of electrons don't want to be close to each other since they're all negatively charged. That kind of falls apart when we talk about single bonds. So when we look at this, those are all 90 degrees. Well, what happens is, in order to actually get those to maximize themselves as far away as possible, what this actually rearranges is, you've probably seen stereochemistry. So this one, just to refresh for you guys, this wedge means it's coming out at you, and the dash means it's going in the page of the paper. What you discover is that 90 degrees is not the maximum distance. Actually, 109.5 is. So these can actually rearrange themselves, which is known as the tetrahedral geometry, and these can actually push themselves away to a 109.5 degree angle to where now they maximize the distance, so there's a minimal amount of repulsion. When it does that, instead of those all being, single bonds, s orbitals or p orbitals, what happens is we generate an sp3 orbital. So what that obviously, if we can look at that, that is 1s plus 3p orbitals. So what's happening here? So if we were to look at carbon, for example, so let's say we have, let's put this over here. If we were to look at carbon, we would have an s orbital with 2 electrons, and then we would have our p orbital with 2 electrons, because we know that the valence electrons for carbon are 4. Now, nature is pretty smart, and what it discovered was, it said, okay, well, we've got this filled orbital here, which is nice, but we have these half-filled orbitals here, and not even anything here. What it discovered was, well, can we take the s orbital and the p orbital and kind of put them on the same plane, generate this hybrid orbital, and now what it winds up doing is we can put 1 electron, we have a total of 4, we can put 1 electron in each one. So now what happens is when we do this is we have sp3 hybridized orbitals. So all that's happening here is nature just decided that if you take these orbitals and throw them all together, you're always going to have 4 with the sp3. Then we can see from this is we have 4 sp3 orbitals. So let's shrink this one down, and now rather than just looking at it and saying, okay, well, how in the world, what does that mean? Let's put that in practice. So if we have a carbon atom, instead of having, when we do these dots, instead of saying, okay, those are just s orbitals or p orbitals, what we actually have are 4 sp3 orbitals. So we have one here. I'm going to draw these at 90 degrees, not with the dashes and wedges, because you can see that's going to be pretty much impossible. But what that shows you now is that we've got 4 sp3 hybridized orbitals with single electrons. What we were seeing before is rather than this orbital that I'm drawing, we just typically we're doing just dots like that. And then we've got that, and then when we add our hydrogens, that's just an s orbital, so that doesn't get hybridized. And then we would just have our hydrogen with an s orbital. And then just like we did before, and now instead of just having the dots that we had before, now we've got circles and things that look like p orbitals. We bring them together. So that's all that's happening, is instead of thinking like in general chemistry, where a lot of times you would just talk about s orbitals or p orbitals, or maybe the introductory of this class, you just talked about those orbitals, they hybridize, and the reason they hybridize is because you maximize that distance, and now everything minimizes the repulsion. All right, so that's sp3. Let's see, what happens if we switch to an sp2? I know this is self-explanatory. I'm just doing this just out of habit. and then we have 2 p orbitals. So let's see what switches here. So if we were to look at that, we would obviously be talking about, we could talk about a carbon-carbon double bond or a carbon-oxygen double bond. So what's the difference here? So this is an sp2. Now we saw before with sp3, what's nice about this, we can think about, is we look at it this way. So if you count the superscripts above this, so S is always going to have 1, you just don't write 1, but a 1 is there. And then the P is going to vary either 3, 2, or they won't write it, but it's a 1. So what that number is going to tell you when you add that together, 1 plus 3 is going to be 4. That's going to tell you how many of those orbitals you're going to use. So in sp3, you're going to have 4 sp3 orbitals. And in sp2, you're going to have 2 plus 1, which is 3. You're going to have 3 sp2 orbitals. Okay. So why does that really matter? Well, if we look at that, we have 3 sp2 orbitals. So we're going to have, let's do them in a different color. So we're going to have 1, 2, let's do this actually. 1, 2, 3. So if I just stop, you can say, well, something's wrong, this isn't working, something's off. You're right. We need 4 bonds to carbon. We can't have 3. So something else is different. So if we have 3 sp2 hybridized orbitals, that means the 4th bond is just a p orbital. Okay, now how does that work and what would that look like? We'll just move this over here. Now what happens in this instance is, we won't worry about this because we kind of saw that. In the sp2, you still have your 4 hybridized orbitals. What happens is you wind up generating, because you've got 3 electrons here, you wind up generating your 3 sp2, and then you have 1 orbital that's left over, because we're always going to have 4, but that is just going to be a p orbital by itself. So that's what's going to happen there. So if we were to actually draw this out, we would have, let's see, we'll use the colors. So we're going to have one sp3, another sp3, sorry, geez, 1 sp2, 2 sp2, 3 sp2. We're going to have another carbon. Each one has to have 3, so that's 1, 2, 3. And then our pi bond, our p orbitals, are going to be the other bond. So you can see that we still have our 4 bonds, but 3 of them are coming from the hybridization, and 1 of them is coming from the p orbital. And as we talked about before, the p orbital is actually above and below like that. So that's going to be an sp2. Now if we just get rid of that, and we get rid of that, and we do an sp, we're obviously going to get rid of 1 more of those. That's going to be there. Do that, and we'll extend that. So that's going to be a carbon. So we'll do our SPs in red. So what that's going to be is we're going to have 1 in between our carbon-carbon bond. Our other one is going to be here. Other one's going to be out there. And then we're going to fill our other p orbitals. I could either draw 1 above and 1 or below, doesn't matter, or like that. I'm going to do 1 above and 1 below just because it fits symmetrically in between. But you can see here once again, to each atom, to the carbon atom, we have 2 of our hybridized, and then to fill the 4 total bonds, we have now 2 p's. So that's going to be our triple bond.